All right, so this first video problem is just a continuation of in-class problems this far. We have means of transportation via a hoverboard and a magic carpet, and their movements are described by these vectors. We deduced that these vectors span the space, so the span is all of R2, and the goal of this video problem is to make a geometric argument showing this, as well as an algebraic argument, and then provoke a little more thought about R3 and how we found that with the given vectors right here, we were trapped in a plane, i.e. Gauss could hide from us. So under what conditions would we be able to find Gauss all the time? So just get right into it. Geometrically, so let's just let V describe the 3, 1 vector and W the 1, 2. So if we look at V plus W, we see that this is our resulting vector right here. And using any linear combination, scalar multiple of V and W, we will be able to take this vector and just kind of scooch it around this whole plane. And this sweeping motion around the plane shows that we can get anywhere within R2, so any linear combination will be able to get us to any point. Therefore, the vectors span the space. So algebraically, we know that a linear combination, which is what this is right here, is just AV plus BW. And we know that it will get us to some X and Y in R2. So the top row gives us our first equation, number 1 right here. The bottom row gives the second equation, and multiple ways of solving systems of equations. In this case, I took equation 2 and subtracted 2 of equation 1, so I multiplied this equation by 2, subtracted them, which yields A is equal to 2x minus y over 5. And we can just sub this result into equation 2. So this yields, upon making the substitution, we find that B is equal to 3y minus x over 5. So we can show that for any x and y in R2, that we have 3y minus x over 5 times our 3, 1 vector plus, oh, gosh forbid, I am so sorry. Our A coefficient is 2x minus y over 5. Our B coefficient is 3y minus x over 5. And this is the 1, 2 vector. And we know that this will get us to some x and y in R2. So for any x and y, we have some linear combination using our means of transportation. So that algebraically shows the vectors span the space. I kind of like the algebraic expression more. And how can we always find Gauss? The reason that he can hide from us is because we're trapped in a plane. The vectors do not get us to everywhere in R3. So the simple answer would to just have 3 linearly independent vectors. It says, how can we change one of them? The issue is that V2 can be written as a linear combo of V1 and V3. So instead of finding a completely new one, I will just offer new means of transportation, everybody's favorite unit vectors. And using these vectors, we will be able to get to wherever we have to go.